Hello, good afternoon, good morning. Welcome to our webinar. Jovan, do you want to say a few words or do you want me to do it?
You can, and I will say for the introduction our speaker today.
For the introduction. Okay, so very well. Welcome to our WITS webinar today, done in partnership with SPE Romania, where we will discuss casing expansion options with Felicia Sirstian at OMV Petrom. This will probably be a series, first in a series of webinars to discuss casing expansion to help us manage sustained casing pressure in wells. And stay tuned for a few, some additional information on that. And then we'll also try to give you at the end of this event a few updates on upcoming webinars that we're working on. Jovan, over to you.
Thank you, Pierre. It's a really pleasure and honor to introduce Felicia Christian, which is a part of my team, and she has a really long history in the oil and gas industry, a lot of knowledge and supporting well integrity in the OMV Petrom in Romania. So Felicia is graduated oil and gas university in Ploiești, Romania, and after that she started as a production engineer in the oil field of West Romania, as in Petrom, Timișoara area. She continued to work with OMV Petrom in Bucharest in the headquarters, and from 2014, Felicia working as a senior expert well integrity engineer in the completion and well integrity department, managing more than 5,000 operating wells and implementing well integrity management all over the OMV Petrom. Felicia is also promoting well integrity management focus on the well dual barrier envelope evaluation, management of the annular pressure, well integrity risk evaluation based on the failure matrix, and support any kind of well integrity events and investigation within the operations. Felicia is also part of SPE Romania committee as a technical support member. She's also contributed to the SPE, publishing many of SPE papers related to the well integrity technology, and the use cases proven with her work and she's projects. So I will welcome Felicia today, and Felicia will talk about casing expansion and the case which we managed to successfully try in Romania. Felicia, stage is yours.
Thank you very much. Thank you for having me here, and I'm glad that I have this opportunity to present you our experience with this method, casing expansion, which is a solution that we tried for remediating sustained annular pressure. As Jovan mentioned, we in Petrom work with huge amount of wells, many of them mature wells, which are experiencing sustained casing pressure. If for a period this sustained casing pressure, if it's below the limit of MAOP, can be managed, it comes a time at the abandonment when this is not acceptable during the abandonment of the well. Our regulatory in Romania does not allow to have any bar in the annular pressure when we abandon the wells, which is normal. Sustained casing pressure, it's a key indicator that we have a problem of the well integrity downhole. I will talk today about B annulus pressure, B annulus being behind the production casing, the annulus behind the production casing. This sustained B annulus pressure can be one root cause, can be the casing failure, which is not the subject for today, but most of the time it's a problem behind the casing, and it's a problem given by the cementation failures. We often see cement integrity compromised due to defects during the primary cementation. It can be microchannels, which are small pads. If you can move to the next slide, Pierre. So we can have microchannels, which are tiny gaps, small pads within the cement matrix that allow fluid migration, often resulting from gas invasion during cement setting, or incomplete mud removal or poor displacement efficiency. We can also have microannuli, if you can give an enter, microannuli being tiny gaps between the casing and the cement sheet, typically caused by thermal or pressure cycling after cementing, or due to the casing movement during the cement before it's settled. We also can have cement debonding, which is a loss of adhesion between cement and casing or formation. All these defects can occur during the primary cementation, but also it can occur during remedial cementation for the same reasons. The solution that we are presenting today, it's referring to this microchanneling, which allows the densification of the cement produced by the casing deformation. So what means this? That we will do a casing expansion, inducing plastical deformation in the casing. And this casing will further compress the cement behind this casing, densifying this cement. We confirmed it for an abandoned well, which already have remedial cementation. If you can go to the next slide. So the principle of the method is to release a calibrate energy to do a plastical deformation of the casing, radial and uniformly 300 degrees. Plastical deformation meaning that we expand the casing beyond this yield point to undergo plastical deformation. And this will most of the time stop the annular flow because it densifies the cement. Let's go to the next slide. Let's see which are the best candidates for this method, because not all the situations are good candidates for this. So for the moment, it's only applicable for the B annulus. So we have to pull out the tubing and to perform the casing deformation against the production casing. Also, we need to check very good the condition of the cement, because we can produce this densification only in a cement with moderate bonding and microchannelings. Also, we need to know very accurate the data, because this data will be part of the calculation of the expansion tools to calibrate correctly the forces. Another, let's say, requirement is that we have a good centralization of the tools. Otherwise, we can perforate the casing on one side. We need also to avoid restrictions, meaning the casing collars. And we need to have detected the leak source to know where is our leak source interval. For this presentation, I will use as success criteria three criteria. Remediation, meaning that we don't measure any annulus pressure in the B annulus. We will use a CBL to before and after to confirm the cement densification, and we will use a multi-finger caliper to confirm the casing expansion, multi-finger before and after. Let's move to the next slide. So I will start with our case study. The well that we testing this method, it's a well for abandonment, an old well, a gas well, which was drilled in 1980. Even during the drilling, we noted fluid losses at 2,120 meters. And therefore, we have challenges during the cementation of the 5.5-inch casing. The top of cement was achieved below this gas layer, meaning at 2,163 meters, which is also below the next casing shoe, the 8 3/4 casing. Because of this, even at that time, in 1981, we performed the remedial cementation of the B annulus between 1,550 and 1,770 meters. You can give an enter to see the multiple enters, to see on the schematic the placement of the remedial cementation in 1981. Enter. Okay. The well produced, we didn't have problems with the B annulus during the production either, because it was not reported, it was very low pressure. The well was put in conservation in 2010. And in 2022, it comes the time to abandon the well. We started by plugging the reservoir at 2,770 meters. More enters, please, Pierre. Okay, that is appearing the remedial cementation. Next enter. So we have a plug of the reservoir in the casing. And then we noted that we have B annulus pressure sustained 6 bars. Not much, but it's important that we don't have this. We did a next remedial cementation in the interval 750-530 meters. Perf and squeeze, normal procedure. Okay. Still, this cementation didn't succeed. As I mentioned, remedial cementation have the same problems if we are having gas influx. So we go further and we tried again in 2023 to do another cement and plug. Squeeze cement at the interval 100 to 300 meters. Hoping that we solve this, and we even plugged at the bottom the well. But then we measured in the B annulus still having 3 bars, 4.5 bars, sometimes 3 bars fluctuating, and we could not abandon the well. So we come back to the well, milled the plug, the cement plug, and here we are with the top of cement in the casing at 400 meters and multiple remedial cementations, which all are failed. No, still pressure in the B annulus. As a final solution, we try this new method, casing expansion in the 5.5 inch. Let's move to the next slide, where we do an evaluation of the leak path, and we also monitor the graph of the B annulus along with all these remedial cementations that we did unsuccessful. We know the source of the leak is at 2,100 meters, where even from the drilling we noted this gas formation, not a big gas formation, but still we have infiltrations. I was mentioning that even remedial cementation can fail depending on the conditions we did an evaluation now of the cement to select which is the best interval where we can do this densification of the cement. Let's move to the next slide where we will see how we selected the interval, the most suitable interval. So first of all, we did a preliminary caliper investigation. So a multi-finger on the casing, 5.5-inch casing, up to 400 meters where we have the cement top. We note here on this multi-finger that we have colors, we have ovalization in the casing, and one of the best intervals would be from this log 180 to 190 meters, an interval of 10 meters. Now we move forward to select also best candidate from the cement point of view. And in the next slide, we would see the cement evaluation, CBL, which in the interval that we already selected from the casing part, we identify 5 meters of cement, which is moderate with microchannels that will allow compression. Also, if you check the top and the bottom intervals, they are better, but of course not still the bonding noted there. However, between 180 and 185, it's the best also from the casing point of view and of the cement point of view. So we now go to the method, how these data were provided to the operator that will produce this operation. And let's see how they would perform the calculation. Let's move to the next slide. So now it's time to design the casing expansion job. The supplier showed us that there are two options depending on the size of the pipe. Our size being lower, we qualified for radial linear expansion charge, meaning single shot expanders, which are shown in the first picture. They have also options for higher casing sizes, which will be dual end fire expanders. Based on the grade of the casing sizes and all the details, they are calculated the expansion charges, which in our cases were 146 gram weight, split in 3 single shot expanders. If you give us an enter, we will see also that we have an orientation pre-calculated table where they are shown depending on the grade, on the weight of the casings, which are the most suitable tool diameters, and which are the default explosive gram weight. Of course, the calculation needs to be separate for the case study that will be done. What is my point is that these charges are calibrated before in the lab, and they were tested so that, as I mentioned, we obtain casing expansion beyond its yield point to undergo plastic deformation of the casing. Let's move to the next slide, where we will see exactly how we did this job. First of all, I would like to tell you that it's a wire rigless operation, only with the wire line. Before the job, must be done a drift run. And to record all that logs that I mentioned, CBL and multi-finger. Now that we have the casing drifted, we can start in 3 runs to shut the expanders. We selected exactly the intervals, 183.5 meters, the first one, second 184.3, and third 185 meters. After this, that some hours interval, we did again the radial, the CBL and the multi-finger to measure how the casing was deformed and how the cement was densified. I would like to make a comment here related with contracting all these jobs. We are here in Europe, and you know that these explosible products are very difficult to be handled with a lot of restrictions for transportations. And therefore we use our contractor for perforation, which already have all these permits in place to work with explosible, to transport them and to bring them from overseas. So this is a tip for whoever wants to use this type of methods, that it's good to frame them into a perforation contract, which already have these permits. So here we have the picture of the single shot casing expanders, 3 of them before they were shot. And if you give a click here, you will see after the job how it was pulled out from the well. Okay, I will move now to the next slide where we will start to evaluate the result of the job. Next slide. Okay, so first of all, we check the pressure at the annulus. We bleed off whatever was there and currently monitor for several weeks and even after 2 months, and the pressure disappeared. So this is the first and the most confident sign of good result. Also, we did also the logging, which were done immediately after the shot of the charges. Next slide. Okay, so this is the multi-finger caliper deformation. First screen it's before, and second screen it's after. You can see clearly the deformation, and also you can see that the difference between minimum and maximum internal diameter suggests that it's a circular and uniform deformation. We also used centralizers, so it was a good centralization. We noted that the internal diameter now it's larger, 4.8 inch, before was 4.58 inch before the job. In the next slide, we will see also the densification of the cement. We can see that our interval is looking much better now. We see indication that in the zone between 183 and 185 meters, it's a decrease in the amplitude. Also, the bond index went from 60 to 70% to a full 100%. So we have good indications also in the CBL. Next slide. I guess that we are almost at the end of our presentation. Conclusions. Although there are challenges and risks to have too much or too little explosive, we have the mitigation is in the strategy of calculating and testing this before in the lab, exactly on the type of the casing that we are using. Also, there is, I would like to mention, it's not written here, but there is a risk of the cement, on the cement. If the cement is too old and it's already brittle, could happen that we do more wrong to the cement. However, in our case, was a recent cement, meaning since months, not if not 1 year, which provide a good behavior during this method of casing expansion. Advantages of the method are that we don't require a rig. This simplifies very much the job and also the cost. There's no additional personnel that is required on location, only the wireline crew. If you compare the cost with other methods which involve rigs and perforations and cementation, the cost is more effective. Also, due to the short duration, in case the well is in production, which is not the case, we are lowering the time of productive time, but also the cost due to the productive crew time. And what we found good advantage is that this can be successful in a well where you already finish all the options with perforating and remedial cementation, as it is our case. So as a conclusion, this method solved our sustained casing pressure in the BE annulus. Now, if you have questions, I'm open to discuss. Thank you very much for your attention.
No, thank you, Felicia. I think it was very good that you actually shared what happened to you with a real life example where the previous attempts had actually failed. I've also noted that the perf and wash that you tried multiple times, those operations did not stop the gas ingress into the BE annulus, correct?
Yeah, correct.
Yeah.
Yeah, and this can be a problem also with remedial cement. Not all the time it's successful.
No, absolutely. No, I thought it was very good. We've had a number of questions online, which is great. So great interaction. We'll start taking a few. I'll stop the presentation for now, and if you want to see it again, then I'll put it back. Or actually, I'll go back to the first slide.
Yeah,
and
maybe we need to refer to some previous slides.
Exactly. If you want to see something specific, we'll go back to it. So question number 1 from one of our users. Here it is. How does the deformation of the casing have an effect on the MASP if we no longer know the remaining burst or collapse pressure? I think it has to do with the plastic deformation of the OCTG and the effect on the collapse in particular.
Normally, if we undergo a plastic deformation, the integrity of the well of the casing should be kept. However, it works that we do a pressure test at a certain pressure so that we can establish a mass. Normally, we in OMV Patron, we establish the mass based on the last casing pressure as per ISO. Of course, there are the casing burst and collapse data, but we also apply this pressure test Normally, also for a cemented interval, perf and cemented interval in a casing, we anyway modify the mask because we really do a pressure test after this remedial cementation. Usually we do it at 50 bars, and that will remain the mask of the casing.
Okay, I think it's a good practical approach, because my experience with both burst and or internal yield and collapse is that it is quite complicated. So for internal yield, you need to factor some degree of support from the cement, which in most cases is very difficult to model.
Yeah.
And for the collapse, absolutely. But then collapse is also extremely governed by your ovalization. So that's then. But yeah, it's a fair comment. Once you've deformed plastically the pipe, you probably have altered its internal yield and collapse ratings.
In this case, it was already compromised by the perf and the squeeze also.
Yep.
Yeah.
Question by Scott Myers. What is the length of the expanded area, and how many expansion intervals, if more than one?
In our case, as you have seen, was the interval was about up to 5 meters, not longer. But we understood that in case the first time we don't succeed, we can try in another interval if we found the same match between the casing suitability and cement suitability.
Okay, next one. And would you say that maybe once you're committed anyway, you in this specific case, you wanted to get a result, you were trying to isolate that flow, how prepared were you to continue expansions until you got what you wanted? So you identified the target intervals, you shot a number of expansion charges in that target area. Did you have a backup plan after that? Were you prepared to continue expanding in the same area if you needed to? I mean, how did you view this?
I think we had another interval upper above 180 up to 100, where was the top of cement. But in case this was not successful, we would need to mill further down towards the source to the 2000 meter, which would have been more costful to mill in the casing and run another CBL to understand where it's another suitable interval for the casing and for the cement to shut again. Otherwise, no other possibility.
Okay. Then we
I think I saw a question was appearing there about the cement integrity. What if it crumbles?
It was one of the last comments, but I'll show it now.
That's a good question, I guess, and I think it comes to the selection criteria, because if there would be a very bad cement, I mean a very old one which is brittle already, I think maybe it's not suitable. In this case, the cement was not too fresh and not too old, being a remedial cement. And was more suitable for this. We don't expect cracking on the bonding, only the densification. I guess this has to be taken in consideration also from the CBL when you select the interval. And if possible to have a not so old cement.
So as a follow-up question on this one, and to keep that good discussion going, so I understand that we want to select an area where we think the cement can be properly, quote
Yeah,
unquote, densified, but so we have a lower probability of success if we chose an area where there's virtually the cement is heavily contaminated. It's not good enough to be densified and become
yeah,
competent.
correct.
Yeah, but so what happens if you try? I had two immediate questions that come to mind. What happens if you shoot the charges in an area of the pipe that's completely unsupported, uncemented? So will it cause
Um,
the casing to fail? And the other question is, if you've done that, we've mentioned acquiring CBL. After that, do we have any idea what the CBL of a of this plastically deformed pipe would be anyway in an area with poor cement? Because it might not resonate exactly the same way, considering it has been deformed. But I don't know. I'm just thinking aloud here.
yeah. I'm thinking the first question. So, what happened with the casing if we don't have cement behind? I think that as per the calculation of the method, it would still be plastically deformed. So, being or not being cement behind, not that we will burst the pipe, but with no effect since there is nothing to be compressed and densified behind. So now this,
So it will
as I
not.
mentioned, if you go to the slide with the selection criteria. It's one of the main selection criteria to have a proper cement
Yep.
behind, moderate, not good but not bad, not
Understood.
missing.
Understood. Okay. Let me show you this one then. Question 2 from the same user that we had initially. How does the casing remain in the expanded condition as metal has memory and will want to return to its original size, as well as to calculate any tubing stress analysis from original condition to expanded condition? So we're back to the idea of having, the physical
Yeah,
properties of the tubular altered by the plastic deformation, which is fair.
to not achieve a plastical deformation, you mean? But I think that for the standard steel casing G55, N80, L80, P110, all these can undergo plastic deformation at a certain stress. So as I said, we will go beyond the yield point so that we have the plastical deformation. There are some materials that probably cannot be plastically deformed, but for the normal wells, we don't use such materials. We are only using these common steel casings, G55, as I mentioned, L80 and N80, P110.
Okay, I think it's
So
a good comment. I do not know how much creep can potentially happen over time in that plastically deformed part of the steel. Probably not much. That is it. Would it be significant enough to alter the shut off? Maybe it's a good question that we could ask.
I think that the contractor that we used
Yeah,
can show their test in the laboratory because they did a lot of tests like this
over
to
time.
be sure they are performing plastic deformation.
Okay,
Maybe next time we will share their experience in more detail, what happened in their laboratory, how they tested this.
very good. And I'll ask them when I visit them. About long-term testing. Question from Simon Spark. Did you consider using the Renegade? So that's Renegade Wireline Services, and Jeff Bartula is on the call, I know. And they have a wireline conveyed solution to this also. So did you consider that?
We did not yet, but who knows? In the future, we may consider because was with the sustained casing pressure we still have.
And that's a good segue for a comment of my own notes, which was, okay, so you presented this specific case, which must have caused quite a few headaches with the time and money invested in trying to shut
Yeah.
off that casing pressure, staying casing pressure. So I would have done what you did. So investing a bit more money on data initially so you can be sure about what went well and you can analyze your success in the future, potentially replicate. So have you considered going slick line only and not even wireline? Because you can do the memory, you can do the CBL, you can do on memory, multi-finger caliper, you can do on memory. The firing of the charges, you can probably do on memory. I don't know if you have enough I don't know how heavy the assemblies are for the charges, but is that something that could potentially allow you to cut costs and replicate and run the same solution and technology for cheaper if you have many wells to remediate?
Yes, I think it's possible. So, in order to lower the cost, we use it a local contractor for the wireline. As I mentioned, specialized also in perforations, and everything was more cheaper for this matter. And I guess also a slick line would work. Yeah, you can do memory logs. Would take a little bit longer, but
And the reason I'm thinking about this, Felicia, is not only because it's potentially a little bit cheaper, it's also because logistically in some areas where bringing a wireline unit offshore on a platform where cranes can be old, etc. Sometimes it's easier to bring something lighter, like a slickline unit, as opposed to having a full
yeah, you're right.
wireline crew.
Mhm.
Yep. Another question from Scott. How were the following considered? One, very hard cement across very hard formation might simply crack the cement and making things worse. And at the other end, softer formation, very soft and contaminated cement may cause, may move the leak radially outwards. So if you were to try to say perform, so I guess you have to check your lithology anyway. And if you had a potentially a formation that would not be competent to shut off the flow, that would be a poor permeable formation, then poor cement, poor permeable formation. You do a casing deformation in an area that could potentially allow flow behind the cement anyway. So then I guess you have it in different words.
Yeah, I guess the comment is fair. Could happen, but you will not choose. If you see that the cement is very hard and it's also very old, as I mentioned there, the cement is more brittle. So we would not choose this interval. It comes to the selection criteria.
Okay.
Uh,
Okay. So
yeah.
would it be fair to say that, based on the Scott's inquiry, that also the lithology where you would place that casing expansion should be considered? So
Yeah, should be considered.
yeah, yeah,
We can
couplings.
should be checked also the lithology there. It's right.
Perfect.
I just want to add something, Pierre. I saw the many comments there, and that the cost effectiveness really depends on the numerous factors what we face and what we experience, depending on which contracts you have with your current supplier. Did you have available? I saw digital slick line proposal and so on. So really depends where you are and which contracts you have, and can you utilize this through the existing contracts to be maybe cost efficient. The beauty of the wireline that immediately your data, you don't need to download and to wait. So also you don't want to spend too much time equally on the job. And also want to tackle the question, did we use any of the investigation more done? Yes, we could run the leak detection and see if there is any leak can be detected, but that is expanding in the much more. We was satisfied with what we get with the data, and we was in talking with the supplier. We was advised that this will be enough to trigger. But yes, we could run maybe fiber optic to determine the leak propagation and to see where will be the best, to choose the best place to run it. Yeah.
Okay. Before we get to the next section, can I use my privilege as a host to ask you about the ovalization that you have reported in one section of the well? Do you know where that came from? Do you have an explanation for that? Do you see it in every well? Did that come as a surprise? How about it?
No, it was not surprisingly. I guess it comes from the using of the mills in the casing, because we milled that area with after, because it was cemented. Also, we have many times ovalization. We have zones with small landsliding, something like this at the surface. So it's often occurring in our wells. We see in the multi-fingers.
Very good.
And they are not suitable at all for this kind of, not to set packers, not to do this kind of operations.
Yeah. So Uchena Makoni is asking, did you utilize leak detection tools in the pre-job planning? If yes, then what was your experience? I also wrote that down as in, okay, you say identify the leak source. Did you run some other logs? Did you run acoustic, spectral analysis? Were you sure about the flow behind casing?
At this well, no, because it was like a very old well for abandonment. But we are planning now a next job where the well is more risky, let's say, and at a higher depth. And here we performed the fiber optic leak detection. And we identified already the interval with this fiber optic. And we are preparing for another job, another trial with this casing expansion. That well that I mentioned also had multiple remedial cementations, similar to this one, but there the pressure is higher. It's like 60 bars, and we cannot get rid of it. Okay. So yes, we experienced the fiber optic for the leak detection. We have good experience, although there are also room for interpretation of this type of logs. Maybe we can also do some more webinars on fiber optic for leak detection, because we see a big potential, but also an optimization which is necessary for the interpretations.
You're officially invited.
Yeah, for sure. It's a very good topic for the next sessions.
Yeah. So question from Bart Joppe. Great results, SCP dropping to 0. Will you continue to monitor for the next couple of years?
This particular well was monitored for another two months and was abandoned already. So yeah, we will keep monitoring it. Keep the gauge there normally for a well like this, which is also on the radar of our authorities.
Very good. So we'll get a long-term demonstration of the permanence, the permanence of the zonal isolation.
Yeah, it's something coming back. We'll notify you.
Yeah. Walter Taju is asking, to put it in numbers, what can be considered the appropriate age of the cement to run this method?
Well, I'm not an expert, but I would say that up to 1 or 2 months after performing the remedial cementation minimum, up to a few years, I guess it's still reasonable. at least this example here had, I guess, 2023, I guess, 2 years.
Okay.
And I would say here that would be worth to evaluate also the type of cement that you use for this remedial cementation. Perhaps there are methods to do a better cementation when you know that you have all these gas migrations in the annulus. I mean the formulas. Our abandonment crews, not sure if they are trained to perform these jobs, remedial jobs, with a special cementation for the gas infiltrations. So this worth also to some attention.
Very good. Okay, here's a question from Bhaskar Murugapan. After the expansion of the casing and densification of the cement, is there any history on how long this treatment will last to contain the pressure? Cost-benefit related question. So I guess we've already kind of engaged a bit in that question, Bhaskar. And at the moment, and other than the labs from service companies providing the service and the any long-term testing they may have had in their flow cells, and what we know of steel, and then the track record. Other than that, I don't know there's any real engineering response to the question on how long.
We expect that at least the plastical deformation of the casing will last longer because it's designated to be permanent deformation. However, we did this example that I'm showing you here was done in November. We will still monitor and see if there's coming back, hopefully not. But for us, as I mentioned, we already spent a lot of money on this well, and to go back to mill to the bottom would have been a nightmare. So this solution was a very easy fix for us in that situation.
Yeah, obviously very successful compared to other alternatives. Question from Ugo Govea. I think it's quite good. It's a segue into, maybe not only for P&A, but maybe to help us manage producing wells. Can it be used?
That's a good point to manage also producing wells, because we start with an abandoned wells to have like a trial and to learn from this. And if they will be successful, we may look for candidates also for production wells if there is needed. For the
Very
moment, abandoned wells as a last resort are good enough. And if they will prove, which already was this example, we'll go also for the production wells.
Question is, did with the production wells, where we have fluctuation of the temperature in there, so if this will affect deformation and bonding to the cement of deformed casing over the time, we don't know. In fact, we don't have a case where we can prove that and share the results, but this is a question mark. If we have multiple cycles temperature, if this will affect plastic deformation bonding together with the casing over the time. Very interesting.
I guess that the thermal effects can be taken in consideration for the cement, also for the plastical deformation of the casing, but mostly if there are other special alloys. But for the standard steel casings, we don't expect, even at the higher temperature, to have the coming back of the plastical deformation.
But it's a fair comment. I think, Jovan, there have been hundreds, potentially more than that of runs in North America. I know they've used the technology in Canada, for instance, to stop venting, vent flows. Okay, and now we have access to all this, track record of potential applications and see how they behave over time. And if the the vent flows were effectively shut off or they reappeared after so many cycles, I think that would be interesting to consider as well. All right. Well, we're going to finish right on time. If there are no more questions or interactions from the live audience, which was excellent today. If nothing else, then I thank you again, Felicia, for coming forward with a practical case where you have showed not only success, but also your difficulties and challenges with the previous operations, managing that well. And I think it shows a very carefully designed test trial, which is fantastic, because then you can potentially apply it to the many more wells that you have. And I think it's obviously of interest to the technical community. And Jeff Bartula with Renegade, the call, it's on you. So if you want to have an equivalent webinar presenting your own solution, then feel free. The rule is simple: bring a client who can do the same as what Felicia did today. Show a real case and what it meant for them and what it did, for a good solution for their own project, and that would make for a fantastic webinar. Part 2 of this. Okay. Well.
Okay. Thank you very
Giovanni?
much for your attention, and see you next webinar.
Yeah.
Thank you, Felicia, for sharing. Thank you all for attending. We are continue with our webinar series. Next is Andre Yugai from ADNOC will talk about more of sustained casing pressure as is theory behind and how it's coming to the sustained casing pressure on the wells. So stay tuned, visit our SPE official page and our LinkedIn page, and stay tuned for more webinars.
Thank you.
Thank you all.
Bye-bye.
Bye-bye.
People ask me why they should join SPE, and what I tell them is that SPE is absolutely essential. Frankly, if SPE didn't exist, somebody would have to go out and create it. When you graduate with a technical degree, a petroleum engineering degree, or other engineering degree, you get a lot of really good knowledge that gets you started on your career, and you learn a lot on the job. But the jobs that we have in this industry, they're really quite difficult. And you've got to have other resources, either to solve specific problems you might be having at the moment, or to better understand how to solve, daily issues that you work on. SPE provides opportunities to learn about new things that people are working on. There are great articles in JPT magazine and the other magazines that we have that are really useful. If you're not reading JPT every month, I tell you it's essential to do that to keep up with the technology. We have excellent conferences where you can learn from people who have solved very difficult problems in our industry. And doing that is just incredibly important and incredibly useful. To me, I don't see how you can be an engineer working in the petroleum industry and not find value in the resources and the opportunities that SPE provides. It's an opportunity to meet people who can help you in the industry. and it's an opportunity to get the knowledge you need to be successful.